Sure, sure. Hello everyone, welcome to this live session on our MOOCs course, Applied Thermodynamics for Engineers. And you probably already know me because whoever is expected to be the part of the audience here are registered student for this course. But still, I should mention that I am Professor Dipankar Basu, an Associate Professor in the Department of Mechanical Engineering at IIT Guwahati. And thermodynamics is one of my favorite subjects, which I have taught here at IIT Guwahati several times at different levels, and also this online course, which presently we are doing. Now, I am supposed to be here to respond to your questions. I have checked the online portal. There are no unanswered queries at the moment. So I have to wait till I get some questions from you via the live chat. You can ask me questions through the live chat, which I guess you can see the YouTube link where which you are following. You can type your questions there, and I shall be trying my best to respond to those questions. Now, as I wait for your queries, probably I can spend some time on reviewing whatever we have done so far. I guess presently we are in the module number 9. We are going to the 9th module of this course. So you have completed 2/3 of the course, and only 3-4 more weeks are remaining for this. If we want to review whatever we have done, then we started with reviewing the courses or reviewing the topics of fundamentals of thermodynamics, where all of you must have done a course on basic thermodynamics. So the concepts of basic thermodynamics were reviewed in that particular module, like the fundamental surrounding processes and cycles, then first law of thermodynamics for closed and open systems, application of first laws, as well as the second law of thermodynamics, its different varieties of statements, as well as the concepts of entropy and exergy, etc. All these were reviewed. Of course, that was quite cramped because I tried to review all the concepts that have been covered in one full course in just 3 or 4 lectures. But again, the objective for that first module was only a review and not introduce any new topic to you. Then in the second module, you studied the thermodynamic property relations. And there we have seen how we can relate the fundamental thermodynamic properties. We talked about different kind of thermodynamic potentials like internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy. And there we have tried to express each of these potentials in terms of measurable thermodynamics properties, like pressure, temperature, and specific volume or density are the properties which can be physically measured for any given system. However, whenever you are talking about something like internal energy, enthalpy, entropy, or Gibbs free energy, Helmholtz free energy, though these are very important potentials to characterize the energy state of a system, it is not possible to measure each of them separately or any of them physically. And therefore, we have to go for some indirect kind of estimation, and that is possible only when we can express them in terms of measurable quantities like pressure, temperature, and specific volume. So there are different types of such relations, particularly the Maxwell's relations that was discussed, and also several other key parameters are introduced. Then we have in the third module, we have talked about the properties of pure substances, which probably many of you have already done as a part of your undergrad thermodynamics. But that is also a very important topic to know, because whenever we are trying to analyze any kind of thermodynamic system, we must be able to estimate the properties of the involved medium. Whatever may be the kind of medium that we are dealing with, a solid or some kind of fluid, that is liquid or gas, we need to know the property values at every precise thermodynamic state. And that is possible only when we have clear idea about the properties of pure substance. So that's what we have done as a part of that third module. So um, topics like the saturation properties, those TS diagrams or PV diagrams, corresponding idea of critical point, a supercritical state. These all have been covered as a part of that module. And after completion of that module, all of you are expected to be able to estimate the state of the properties of any given fluid for any given thermodynamic state, whether it is a compressed liquid state, or whether it's a mixture state, whether it is a saturated vapor state, or it's a superheated vapor state, or maybe a supercritical state, using the thermodynamic property relations that have been studied in the previous module, and also all those property tables and charts introduced in the third module. You are expected to be able to estimate relevant properties like enthalpy, entropy, internal energy, etc., can be estimated. And once you are able to estimate these properties, you are in a position to analyze any thermodynamic system using the fundamental laws of thermodynamics. And that's what we have done from the fourth module onwards, as we focused on thermodynamic systems. So in the fourth and fifth module, we have talked about the air standard cycles, or more specifically, I should say, we focused on internal combustion engines. So in the fourth module, we analyzed air standard cycles, which are the ideal cycles for different kind of internal combustion engines. The Otto cycle is the ideal cycle for any petrol or gasoline based device, whereas the diesel cycle is the ideal cycle for any diesel based device. We have also talked about the dual cycle, the Joule cycle or Brayton cycle, which is the ideal cycle for gas turbines. And we have also done a bit of comparison between different kinds of cycles, several numerical exercises, because this is something from where we started talking about the application. This course is of applied thermodynamics, and this fourth module is the one from where we started true applied thermodynamics. So while we talked about the ideal situation in terms of the air standard cycles in the fourth module, um, we talked about several practical aspects as a part of the fifth module when we talked about the real processes or real cycles for reciprocating engines, where the air standard cycle, which has numerous assumptions, quite a few assumptions were relaxed in the form of the fuel air cycle. Then we also talked about practical scenarios like heat losses, like the finite time requirement for opening and closing of valves in any reciprocating engine, etc. And accordingly, we have seen that now whatever may be the air standard efficiency of a given engine, there may be several reasons that the actual efficiency that we are achieving in practice is way lower than that. So what may be the possible reasons? What are the ways we can eliminate or at least minimize some of those factors that have been discussed in this fifth module? So fourth and fifth module somewhat go hand in hand, where we talked about the internal combustion engines, or I should say reciprocating type internal combustion engines. Whereas in the sixth module, we have talked about the rotary type internal combustion engines in the form of gas turbines. The Joule cycle or Brayton cycle was covered earlier itself, and the Brayton cycle is the ideal cycle for a gas turbine process or a gas turbine. But the simple Joule cycle is of course an idealization, and there are several kinds of improvements possible over that, like intercooling, like reheating, regeneration. We have explored quite a few of those. We have talked about starting from the simplest possible cycles to much more complicated cycles, all as a part of this module number 6, where we talked about the gas turbine cycles. So module number 4, 5, and 6 all in a way are related to the internal combustion devices. Module 4 and 5 talks about the reciprocating type internal combustion devices, and module 6 talked about the rotary type internal combustion devices. And what do you mean by internal combustion? Internal combustion means where the combustion of the fuel is taking place inside the device itself or inside the system itself. Like think about what happens in a typical say two-wheeler engine. You purchase fuel from the fuel station, maybe petrol, which you put in there, and when the engine is operating, it drags air from surrounding, and then the fuel and air interact with each other And we have the combustion process, during which the chemical energy of the fuel is converted to the thermal energy, which is subsequently transferred to the shaft in the form of mechanical energy. However, this entire process, that is chemical to thermal energy conversion, then thermal to mechanical energy conversion, all this happens inside the engine itself. You don't need to have any separate combustor. Of course, in case of a gas turbine, that is not the case. In case of a gas turbine, we can have both internal combustion as well as external combustion type gas turbines as well. Like we can have a separate combustor where fuel and air are supplied, and the high temperature gases are then supplied to the gas turbine. So that is more an external combustion type device, uh, or, or open type. But we can also have the closed type gas turbine devices as well. Uh, by the way, I'm still waiting for your queries. If any of you are available online, I can see some of the participants, some of the students are here online. Write in the online chat. I shall be happy to respond to your queries. Now, in the 7th module, we talked about a completely separate category of devices. That is, we talked about the steam power cycles. So as a part of steam power cycles, the Rankine cycle, of course, is the one that was covered. We actually talked about the vapor power cycles, conventionally called the vapor power cycles. But most of the, while it is possible to have vapor of any other kind of fluid, but most common vapor that we use is nothing but water vapor, and that's why these are also called the steam cycles. So there we talked about the Rankine cycle, which is the fundamental cycle used for power generation. You have seen it is also an external combustion type device where we have a separate boiler where we are supplying some fuel, and the fuel is burning to produce high temperature. Now, one important thing to note, one important difference to note compared to those earlier category of devices like internal combustion engines or gas turbines, that there we don't have any secondary medium. The fuel itself burns, produces high temperature gases, and the gas itself acts as the working medium in the engine during power production. However, in case of a steam turbine, we supply some kind of fuel, which may be coal, which may be something else, and that fuel itself produces high temperature gases similar to the internal combustion engines. But the gas is not the working medium. Rather, the energy from that gas, the thermal energy, is transferred to the actual working medium, which commonly is in a liquid state, and it absorbs the energy and gets converted to a liquid vapor mixture. Like when we are using water as the working medium, so water gets converted to a mixture, saturated mixture of liquid water and water vapor, generally at high pressure, reasonably high pressure. And then that mixture is taken to a boiler drum. In the boiler drum, they are separated, and the liquid phase comes back with some refilling, comes back to the boiler for the next step of steam generation, whereas the vapor phase, which has been separated in the drum, that goes to the steam turbine. In the steam turbine, it provides the work by rotating the blades. When the steam, high temperature steam passes through a nozzle first, there its thermal energy gets converted to kinetic energy. Then that high velocity steam strikes the turbine blades, and the blade starts to rotate. So it makes the shaft also rotate. And the shaft externally is connected to an alternator or generator. So it also rotates with the same velocity, with the same frequency as the turbine. Accordingly, we get the electrical power. But the steam, after passing to the turbine, goes to a condenser where the waste heat is being taken care of. It is being extracted, and it goes back to its original state so that it can come back with a boiler. We generally have a pump in between to maintain the pressure of the system. It's a forced flow system, so we need a pump. This now the steam that passes to the condenser, it of course still has some energy left, which is being rejected, and the condenser water takes the heat So the temperature of the condenser is a very important parameter in deciding the net work output as well as overall efficiency. And also the highest temperature of the system, which is the temperature of the mixture and the drum, is important because these two temperatures, we know that from Carnot cycle, the efficiency depends on the highest and lowest temperature. So these two temperatures are of direct relevance, and by changing the highest temperature, the lowest temperature, as well as the highest pressure, we can modulate the efficiency of the system, the work output of the system. Maybe if some back work is required in the form of pump, etc., those can be done. One very important difference between the internal combustion engine and the internal combustion engine, I should say gas turbine, which is not an internal combustion in a way, but a very important difference between the gas turbine and the steam turbine is that in case of gas turbine, the gas needs to be pressurized before it can go back to the what I can say, it can go back to the combustor, or often the waste gas are released to the surrounding. So the fresh new air that is being drawn from the surrounding needs to be pressurized and then it is sent to the combustor. But pressurizing a gaseous medium is always costly means costly in the sense that it requires very high amount of work, because from your basic thermodynamics role you can remember that for a steady flow device the work requirement is integral vdp, that v is the specific volume. For a gas the specific volume is always high, so for a given pressure difference this integral vdp work will be very high. Now compare that for the case of a steam turbine. In case of a steam turbine, the state of the fluid at the exit of the condenser or inlet of the pump is that of a liquid. Specific volume of liquid is very small, so that integral VDP work generally is very small, and therefore that back work for a steam turbine is always very small, whereas the back work is always a big concern in case of a gas turbine. Now there are several improvements possible in case of traditional Rankine cycle as well. Like we can have the reheat cycle, we can have the regeneration cycle. We have all discussed all those as a part of that module number 7. And generally a reheat regeneration cycle, sometimes with multiple steps of reheating, we that's what we have in practical power stations nowadays. And in the 8th module, which was covered in the previous week, we have talked about the cogeneration and combined cycles. Now, it is very popular nowadays that we generally combine two different kind of cycles to extract even more power from a system. Like we can combine the gas turbine and steam turbine, or we can combine something innovative like an MHD cycle with a steam turbine, so that there will be a topping cycle and a bottoming cycle. So the topping cycle will be absorbing heat from some source, then it will be producing some work in its own turbine, like if we are talking about gas turbine and steam turbine plant combination. Then in the gas turbine will be the topping cycle, so it can extract or it can go through the combustion process, that high temperature gases will be used in the turbine to produce energy. But still when it comes out of the turbine, still has very high temperature left in it. It's very high temperature and therefore lots of energy left in it, and that energy will be utilized in a waste heat recovery generator, where the waste heat from these burned gases will be transferred to liquid water to produce a water vapor mixture, liquid water and water vapor mixture, and then the water vapor being separated can be used for power production in a steam turbine. So we are simultaneously getting power production from gas turbine and steam turbine. We are also minimizing the energy loss, particularly from the gas turbine cycle, because if we are not able to utilize that heat in the waste heat recovery generator, that heat will be going to the surrounding, so it's entirely a loss. So this kind of combined cycle or cogeneration cycles allow us to reduce loss, accordingly increase the total power output, and of course the overall efficiency of the plant. We have already seen how the combined efficiency of a cogeneration plant or a combined cycle plant can be greater than both the individual components. In fact, not we may be having more also. It is possible to have even 3 stages also, though rare in practice. So module number 4 to module number 8, we have covered different types of power producing devices. And mm, what I can say, we have talked about internal combustion devices, we have talked about gas turbine kind of external combustion devices, as well as the steam turbine kind of external combustion devices, and their combination in the form of combined cycle as well. Now, the ninth module, which presently is going on, in this ninth module, we are actually talking about a completely different kind of cycle, which is the refrigeration cycle. So instead of power producing cycle, now we are into the power consuming cycle. I guess you have already started going to the video lectures there and may have also taken a look at the assignment. So the refrigeration cycle is particularly the vapor compression refrigeration cycle can often be viewed as the reverse of the Rankine cycle, where power is supplied and we get the heat absorption as the desired output from the system. And instead of efficiency for power absorbing cycle, we use the concept of COP, coefficient of performance, to characterize such systems. Now, once the module number 9 is done, you will be going to module number 10, which is a slightly smaller module, where you will be talking about, or rather we shall be talking about the gas mixtures. Very simple properties like gas mixtures, Dalton cycle or Dalton's law, Amager's law, that we shall be talking about. Then in the ninth module, again a very important one, we shall be talking about the gas vapor mixtures. Like in module number 8, while our focus will be module number 10, sorry, our focus will be only on a mixture of ideal or non-ideal gases, but not vapor. In module number 11, we shall be talking about mixture of gases and vapors. What is the difference between them? The gases generally are ones for which the prevailing temperature is way above the critical temperature, so that only by compressing them we can't convert that to the liquid stage. Whereas for the vapors, we are generally working at a stage close to its critical point, and therefore by compressing them we actually can convert them to vapor by staying at the same temperature. The application of this gas vapor mixture is in the field of air conditioning. So we shall be talking about the air conditioning processes. Different kind of air conditioning processes will be deliberated as a part of this module number 11. And finally, in the last module, we shall be talking about the chemical reactions. We have already seen how important chemical reactions are in the scope of thermodynamics, because in case of internal combustion engines or gas turbines, we only are having combustion to extract the chemical energy from the fuel and convert that to thermal energy. In case of Rankine cycle or similar steam power cycles, again, the whatever fuel you may be using, that goes through the combustion process to extract the chemical energy and convert that to thermal energy. And therefore, it is important that we have some basic idea about the thermodynamics of chemical reactions or chemical processes. So that effort will be done as a part of the 12th and last module of this course. We shall be having one more live session towards the end, maybe in the 12th week, so that if any of you have any further query or any specific query about those modules, that can be taken care of. Now, here I'm waiting for quite some time, though I can't find any questions from your side. There are quite a few participants available online, but I don't know. You don't have any questions, or you are not able to ask. Maybe I'll wait for just 1 or 2 minutes. If I am not getting any question from your side, then I have to wrap this one up. By the way, if once you are going to the lecture videos, whatever queries you have, you can always ask that in the course portal. At the same time, you can also give your feedback about whatever you feel. You can also directly write to me. My mail ID and the similar contact details are available on my personal website on the IIT Guwahati web page. So you can always write directly to me as well as can write in the course portal, which can be taken care of immediately, and I shall be trying my best to respond to your queries relevant to this course, of course, because I am interested with the responsibility of teaching you applied thermodynamics. So any question associated with the content of this course, I shall be happy to respond to you. So no queries are coming from your side, and we are live almost for 25 to 30 minutes, more than 25 minutes. What should we do? Should we wrap it up? Thermodynamics is a subject which is very, very close to our day to day life. Of course, all of you are studying thermodynamics as a part of your engineering curriculum, and you are studying more like engineering thermodynamics. But along with the basic thermodynamics and applied thermodynamics, thermodynamics has a huge philosophical value as well. You can relate almost everything that you do in day to day life with thermodynamic principles or laws of thermodynamics or the concepts of terms like entropy, etc. Like whenever we are living very disciplined life, then probably we are going for a low entropy life. Think about, say, if you are staying in once you are coming back to your room, hostel room, or your house after attending your classes in the college, and if you have the habit of throwing everything away, like your bag and your dresses and anything, then next morning when you are again about to go back to the class, then you have to search a lot. But where is my pen? Where is my copy, etc. So that can always be related to a high entropy life, and you are losing lots of entropy. Whereas if you are taking a bit of time to keep things in an arranged position, then next morning you know that exactly where is your book, where is your blue copy, or where is the pen, and so you are hardly losing anything. Those time that and effort that you are losing in searching for those things can always be related to something like irreversibility. Now, these are of course not engineering. I am talking about more philosophical principles, but these things happens at higher level. Thermodynamics is always related to uh, what I can say. Thermodynamics is always related to the philosophical principles or philosophy of life. But as there are no questions, so I guess we can close down this live session now. There are no students, or students may be there query over last half an hour. So instead of waiting any further, I'd request our technical team to stop this live session now. I am assuming that you are not having any questions at the moment, and you are satisfied with whatever being taught as a part of the lectures, whatever being discussed through the portal. So that's good to know for me. I hope we shall be able to meet again during the next live session. Till then, take care of yourself. Thank you very much.